Okay, this is lecture 5, and we are in this lecture looking at the position analysis, which we started looking at in lecture 4. But in lecture 4, we started with graphical methods. Um, in this specific lecture, we are really more trying to do like mathematical formulas more than a graphical technique. So, because if you have a mathematical formula, a mathematical equation, you will be able to look at the equation and you can plot it on Excel or MATLAB or whatever, and you can look at the different parameters that affect or that impact the motion of the output link or whatever linkage you're talking about, and you'll be able to study the effect of those parameters on the performance of the linkage, this sort of stuff, with just simple programming of a computer package like MATLAB or something, right? So we are looking now at the position analysis with analytical methods, and just wanted to say here that with analytical methods, we can either use trigonometric functions, so we can use a little bit of trig, or we can use the vector methods, possibly complex number. No, theory a bit, like, just, but not much. Like, it's not a mathematical course. We just use some like enough mathematics to support what we're trying to do. So we'll just start looking at the trig and how it is used for the position analysis of linkages. I just hope you still remember your trig identities, the simple ones, and because you are going to use them a fair bit in this course. So I don't know if I need to put those values down, but maybe I can just say some trig stuff. I can say sine, we say like sine 0 is equal to 0, sine pi over 2 is equal to 1, uh, sine pi is equal to 0, sine 3 pi over 2 is equal to minus 1, and then sine 2 pi is back to equal to sine 0, and then also the cosine identities, like if you remember cosine 0 was 1, correct? And then you have then cosine pi over 2, and this is 0, and cosine pi is equal to negative 1, and then cosine 3 pi over 2 is 0, and then cosine 2 pi back to cosine 0, which is 1. And then the simple rules, such as how to expand a cosine function. So if you cosine A plus B, just cosine A sine B minus sine A sine B. And if this here in the middle was minus, would have been plus over here. So just opposite. And then you have the sine expansion as well, A plus B, just sine A cosine B plus cosine A sine B. And if the in the middle here the sign was negative, I would just have negative here as well. So this is simple things you need to remember. You possibly need to remember also that in a triangle, because you have some, like when you do positional analysis of a linkage, you really have to deal with a number of triangles, and you try to link the sides together with the angles and so on. So if I have my angles here and I have my sides like that, just don't forget that a squared is equal to, when you calculate a squared, right, you get into the triangle from one end, then that's equal to the other side squared minus 2 the product of those sides cosine the subtended angle. So here I have b squared plus c squared minus 2 bc cosine the angle A, right? Type thing. So this angle here, okay? And this applies to any other link as well. And also I have the sine or any other side as well. So I can say b squared is equal to whatever, c squared is equal to whatever, and always look for the opposite links in the subtended angle. Now, also you can use a sine rule, like if you say sine A over the opposite is equal to sine B over the opposite, which is also equal to sine C over opposite. So this simple like sort of trig identities, you are going to need them a fair bit. So that's why I put them here in front of you. But I would imagine that you also need to commit them to memory or write them, like have them in front of you all the time, and possibly can take them to the exam as well, because in the exam you'll be allowed one double-sided formula sheet if you like. So you can take those as formulas with you. All right, so I'll just let's start with one example here, not waste longer time. Then we'll say, okay, now I have example one. If I have, if you remember my slider crank linkage, that's R2 and this is R3, and I'm after the distance X, and this angle here is theta 2. I can refer to this point as A, this point as B, right? Okay, okay, this will be my point B, but I'm going to use this space. So that's point B over here. Now, I want to be able to relate those equations together, or to relate those sides, the sides of the triangles together with some trig equations here that will help me obtain a function for my x variable. All right, so if I say R3, all right, so if I go R3 squared, that's equal to R2 squared plus x squared minus twice, right? R2, correct? X cosine the angle between them, which is equal to theta 2. All right, so this gives me one equation. And in fact, that's a quadratic in terms of x, which I can endeavor to solve. So I can rearrange this equation by saying that's x squared minus 2 r2 cosine theta 2 times x, right, plus r2 squared minus r3 squared, that's equal to 0. Very much similar to when you say ax squared, right, if you remember, plus bx plus c equals 0, the quadratic solution which has roots x equal to minus b plus or minus square root b squared minus 4ac over 2a. Remember, something like that on the side. All right, so let's apply this here to find an expression for x. So I can now simply just say x would have been equal to, now I have a is equal to 1 in my case, right? A is equal to 1, b is equal to minus 2r2 cosine theta 2, and c is equal to r2 squared minus r3 squared. I just apply these values here to find the roots of x. So minus b will be 2r2 cosine theta 2 plus or minus square that for r2 squared cosine squared theta 2, and then take away 4 times the product of a, which is 1 times c, so it's 4 r2 squared minus r3 squared over 2 times A, which is 1, so over 2. And now if I divide everything by 2, then this will cancel out for me. And then my expression will be R2 cosine theta 2 plus or minus, and open this here. So we can say it's R3 squared, just arranging inside a bit. When I multiply here, I'll get a positive sign. Then I can say, okay, minus R2 squared, in brackets, I can have 1, right? And I can have also minus cosine squared theta 2. All right, so that's some expression I can have here. So this will be R2 cosine theta 2 plus or minus square root of R3 squared minus R2 squared sine squared. So this is R2 squared sine squared theta 2. And I can rearrange, if I wanted to have, I just realized this term has R2, that's millimeter or like length or meter, whatever. I need to show that I have also the same unit here. I can take maybe R3 as a common factor. Simplify inside, so R2 cosine theta 2 plus or minus R3 brackets and the square root 1 minus R2 over R3 squared sine squared theta 2. This gives me an expression for the distance x. All right, now I want you to just realize we have a plus or minus here. All right, what does this mean? I'm sure if you remember that before we looked at the possibility of having two different assemblies. So I would possibly have another assembly. So if this would be the plus, my assembly one is a plus because assembly one gives me a large value of x, where the second term is added to the first term. The second assembly would be the minus one, will be relevant to minus, and because this one will give me a negative value for x type thing, because it will be on the other side. So this is the other possibility for the linkage. Like you can say that's assembly number 2, and here, and this is my original one is assembly number 1. All right, so hence the idea behind the plus and minus. So there is a physical meaning for this alternate sign here, plus or minus. All right, so my design, obviously the one I initially drew would be a plus, correct? So for my linkage here, I'll say possibly to assert, I'm going to write to assert that. I'm going to say for my linkage, x is R2 cosine theta 2 plus R3 1 minus R2 over R3 squared sine squared theta 2. This will be my equation, the equation for my link. And if you wanted to plot this, you can plot it now because x just function of the one variable theta, and you can assume any values to plot that if you wanted. So you can go theta from 0 to 2 pi or something, and then pi in the middle, pi over 2 and 3 pi over 2, and find the values for x, where x is going to be max and x is going to be minimum, and we find this difference here, which is the stroke, right? And you would expect this to be equal to R2, right? Because when you go back and look at your linkage, when theta 2 is equal to 0, you'll find that like at this position here, you can get a different color here. So here, if theta 2 is equal to 0, you'll find that B is as far as it can get. That's one extreme position. If theta 2 on the other side, theta 2 is equal to 180, you'll find that B will be over here. So prime and 2 prime if you like. And the distance between them, this will be the stroke. And you'll see the stroke distance between the two extreme positions or two stationary positions would be equal to twice the crank, if you like, which is like the throw of that slider or the crank. So now we can say over here that if I want to plot that, so that this will be maximum when theta 2 is 0 and point B is as far on the right hand side as possible. When it's equal to pi, it will be as far on the left hand side as possible, point B, and then this will be here. So I can possibly have and say maybe it will be something like that. I mean, if you plot it, of course, you get a better. Of course, it should also be more like symmetric around the point, the middle point, because it just repeats itself on the other side. So over here, where point P is equal to, like here, this you expect the slider velocity to be 0, slider velocity will be 0, slider velocity will be 0, because they are extreme positions, stationary positions, right? We call them stationary positions before. These positions are just stationary positions, right? Type thing. Between them, you get the stroke. All right. What about, so this is about the slider and the way it moves and whatever. And then how about the other link I have, which I didn't look at? Link number 3. Okay, so let's, it's part of the linkage, and possibly you will need to find the position of this link against the angle theta 2 because it's part of the linkage, and maybe it is connected to a link which drives part of a machine or something like that. So if we try to find an expression for this other link, which is of course I'm referring here more to the connecting rod. So I'm referring more to the con rod. So obviously I have, so this is R3, that's the con rod, and R2, and I have this angle theta 2, this is B right over here, and okay, and this was my distance X, which I dealt with previously. So now I know my distance X, and I need to be able to talk about this link and say I know where it is, right? So I know 2 points on the link. I know this point B, I know point A type thing, but I want to also talk about the angle of this link, which angle is going to take, so type thing. So what if I decide to take this angle here? I'm just going to refer to this angle as the angle phi. And I could have taken the angle inside if I wanted to. But for some reason, when I looked at the linkage, I decided to take phi because as phi increases, as phi will increase, if it is increasing, then this means R3 is actually rotating counterclockwise, and because phi is increasing, I get a positive velocity, angular velocity, because it's the increase of displacement of is increasing the position, so it gives me a positive velocity type thing, which makes sense to me. So normally, if the velocity is counterclockwise, we take it as positive. If phi was decreasing, then later on I'm going to get negative velocity in this case because the angle is decreasing, and also counterclockwise velocity will always take it as a negative when we take a numerical value for it type thing. So phi sounds to be a reasonable angle for me, but I'm sure if you take other angles you get similar results. So okay, so for this angle phi, I want to find an expression for angle phi. I go back and do my equations again, use the triangular relationships again, the trig equations again. So possibly one of the equation I had previously was the R3 equation, right? I had R3 squared was equal to r2 squared plus x squared minus 2 r2 x cosine theta 2. I did use this equation to find my x. I created a quadratic out of this equation to find an expression for x, and this was very useful, this quadratic, because it gave me a plus or minus, and it sort of hinted to me there was another possibility for to assemble the same linkage. All right, so now if I wanted to have another uh, equation, because I'm after phi this time around. So if I say r2 squared, just look at the thing from the other direction, r2 squared would be equal to, again, in this case, I'm going to say it's r3 squared plus x squared minus 2 r3 times x cosine the angle between them, which will be pi minus phi. That's pi minus phi. This angle here is pi, take away phi. All right, so I can now clean this a bit because I have two things I need just to expand and get rid of pi. So I'm going to say it's r2 squared, r3 squared plus x squared minus 2 r3 x cosine. Here I have cosine. I want to expand that. Will give me cosine. Cosine pi is -1. So this will be positive, and I'll have cosine phi over here. All right, okay. So the other term will be 0 because it will be sine, and sine pi is 0. All right, so I have those two equations now. I can work together to get rid of x and find an expression, because x was another variable and I worked out x already. Somehow I need to just after phi this time around. Now, how to deal with this equation? Okay, one possibility here is to say, okay, what if I decided to add the two equations together? So if I add 1 plus 2, what will happen? If I add 1 plus 2, if I add 1 plus 2, I'll have, let's do this together, see if this will give us a solution or lead us to closer to a solution. So I'll have r3 squared plus r2 squared. On the other side, I'll have r2 squared plus r3 squared plus 2x squared minus 2x, open brackets. I'll have cosine theta 2, correct? I'll have cosine theta 2, and I'll have minus, but okay, so cosine theta 2 multiplied by r2, I don't want to forget that, right? And I took minus outside, so I'm going to insert r2 in here. And then on the other side here, I took 2x as a common factor. Then I'll have inside here plus r3 cosine phi. All right, so this will be r3 cosine phi because I decided to take 2x outside. And inside here, because I'm adding, I've decided to take minus outside. So this here should be minus as well. So otherwise it would change my equation for me. I don't want this to be the case, because now when I multiply minus times minus, I'll get positive as I have over here. All right, okay, that's positive. And this one is minus when I multiply it. Okay, so now I can tell that those will cancel out as you move them around. X will cancel with the square, 2 would cancel with that, and then in this case I can move things around a bit, and I can now expand this if I want to, just to look at a little bit more in a clear way. So I can go minus this will, I'll only have x remaining from this end, then minus r2 cosine theta 2 plus r3 cosine phi. Okay, this is good news, because x from here, I have an expression for x. This was x. I'm just going to copy this underneath. And in fact, I can even rearrange my terms a bit. by saying, okay, so I can put cosine phi on the one side of the equation. So I'll have R3 cosine phi. On the other side, I'll have R2, correct? I have R2 cosine theta 2 minus x. Right, okay. So this will be minus x. So now that's R2 cosine theta 2 minus x, which was R2 cosine theta 2. I had plus or minus, minus or plus, right? The square root R, I had R3. So this was R3. And in brackets here, I had 1 minus R2 over R3 squared sine squared theta 2. This was what I had up here. Okay, so this is what I had up here. All right, so now what will happen is, so this was my, so this gives me two possibilities for if I just, because x had a plus or minus, and that's negative x. So if it was plus, so with assembly one would be minus, and this would be assembly 2, right? Well, phi will be on the other side of the y-axis or whatever. So I'll have a different, and this will be assembly number 2, right? Okay. So I'll just clean this a bit by canceling those. So, and R3 will cancel. So cosine phi is minus for assembly 1 and plus for assembly 2, and just here 1 minus R2 over R3 squared sine squared theta 2. For assembly number 1, cosine phi is negative 1 minus R2 over R3 squared sine squared theta 2. All right, okay, so that's here an expression for the angle phi. Now, so phi will obviously be cosine minus 1, this specific expression. And if I get it, I plot that. So it's when it's negative here, because the negative tells me that phi is going to be in a specific range where the cosine is negative. And possibly, if you remember this specific, the quadrant, you know, situation where all like are positive. Here sine was positive, and here cosine was positive, and tan was positive, right? This sort of thing. So it tells me phi is going to be in the section of this, like if you like plane where it's negative. Phi is going to be negative. So phi is going to fall over here. This, and of course, because my drawing itself, my phi was like that. If you remember, the way I draw phi was like that. Okay, so phi is going to be something like that. So phi is going to fall between the second quadrant and the third quadrant all the time. If the mechanism changes position to another, so if it's underneath, like if this is like here, and then phi is going to be in this range above pi. So it's obvious now phi is going to be in a specific range where it's really will be between pi. So here, like phi is equal to pi, and will go back up like less than pi as theta 2. So when theta 2 is equal to 0, phi will be equal to pi when this is quite flat. And then as theta 2 acquires a value above 0, phi will be reduced a bit. So we'll go into this quadrant, and then till theta 2 is 90 degrees. When theta 2 is 90, you expect to get maximum value of phi. When theta 2 here is 90, because you get 1 over here, so you'll get the maximum value of phi. And then, or if you like the minimum value of phi, will be minimum, phi minimum. And then as the crank rotates further, phi is going to now to increase again till it will become, when this is 180, will be 180 again, and then it will keep going above 180 as the crank goes below, starts going below the x-axis. Phi will be above 180, so will be here. So you can tell that phi is going to remain in those quadrants. In fact, the question of how to calculate an angle on a computer, on a calculator, is always asked. Should I use, the question says, should I use the inverse cosine or inverse sine to calculate the angle? And the question is posed when you have a situation as such as this one, when you have the angle, you have cosine phi, and you want to see if this would be sufficient to calculate the angle accurately or not. Okay, so the answer to this question would is something like that. If your, let's say, let's give them, name those quadrants. So 1, 3, quadrant 4. So if you are sure that your angle is going to fall in this range or in this domain, if you like, you can use inverse sine to calculate the angle. So sine minus 1 would be okay, right? And sine minus 1, it will give you either a positive value for the angle or will give you a negative value for the angle, and you'll be able to tell where the angle is on your um, plane. Now, if you are certain, so if you are certain your angle falls here, use sine, inverse sine. On MATLAB, I think this angle is called A sine, right? On MATLAB. All right. Now, the other thing is, if you are certain that your angle falls here, right? You can use here, you can use cosine minus 1 to get the angle, right? And should be okay. On MATLAB, this is a cosine. All right. So if you have any doubts that your angle is going to fall here, or you are not sure where the angle is going to fall, like the linkage is quite complex and you don't know exactly what will happen. It, like in robotics, can take any value. Like in linkages, you like sort of, you can tell somehow that the range of this angle is whatever, but in robotics can be quite difficult. But in this case, if you are not sure, or this quadrant, like this quadrant, or not sure, use both. So you have to use calculate. In this case, you calculate sine and cosine, and then so calculate sine and cosine, calculate sine and cosine, and then and then use and then use a tan 2, this function a tan 2 on MATLAB, or many, like computer apps applications will give you that. So here usually you'd have the sine, and here you'd have the cosine on MATLAB, and this will take into account both sines and cosines of those values. It will take the sine of both the sine function and cosine function, and will match those together, and like on the quadrants, and will be able to tell you your angle is equal to that. So if in doubt about the angle, or if you are in the third quarter, angle is going to go into third quarter. Going into third quarter means the angle is going to be above 180, right? And below 270 type thing. So over here in the first two quadrants, the angle is between minus 90, is going to be between minus 90 to 90. Over here from 180 to 0, this sort of range will use minus. All right, so use the cosine minus 1. So my angle here in my back on my example, now as my angle is going to be in this range, so it's going to go into Q3. Right. So I need to calculate also, I need to calculate a sine expression with the cosine expression I had calculated. So in this case, I'll just, okay, let's calculate the sine expression. So my linkage is like that. This is R2, and this is R3, and this is phi, and so this here with theta 2, and so this is pi minus phi, this angle here. So I can use the sine rule by saying that sine pi minus phi divided by the opposite, which is R2, will be equal to sine theta 2, divide this by the opposite, which is R3. So over here, that's sine cosine minus cosine sine. So this will be sine phi will be equal to R2 over R3 sine theta 2. Right? So now at any value for theta 2, I can plug the value over here to get my cosine phi, and then I plug it here to get sine phi, and then both those together in a tan 2. So I can say phi is equal to a tan 2. Now sine phi, comma, cosine phi, and you'll be able to plot phi against theta if you like, this way type thing. So you'll find that of course phi will have some value which is will start by, as I said earlier, will start by pi when the thing is quiet. We'll start by pi, and then will be reduced a bit, right? And then we'll go back to pi, and then we'll go above pi as the crank goes into the other below the x-axis, and so on and so on. So we'll be able to plot this actually here. So you'll find the value of phi will have some minimum value and some maximum value, right? And in between it will be like pi type thing, just between. So start by theta equals 0 here, and then theta equals 0, and then theta equal 2 pi, and you can plot here to see what, like, see how you imagine phi will look like in this space type thing. All right, so that's one thing. Also, I wanted to say here, you have situations that the equations I get, again, they give me inside when I do my position analysis, like I like with equations, I get a good insight into the linkage and whether it will work or not with the specific dimensions and length of different links and stuff. And just enough for me to look at the expression for the sine function here. And this just gives me lots of information because it tells me straight away that R2 has to be less than R3 to get a linkage that moves, right? Just by looking at this, because it says R2 has to be less than R3, has to be, right? So it cannot be equal, cannot be greater. So if it's greater than, because if sine at some point in time, if R2 was greater than if R2 was greater than, I'll write this equation and maybe we'll write a couple of comments on it. So sine phi was equal to R2 over R3 sine theta 2. You know that maximum sine is equal to 1, which is sine 90, and that pi over 2 sine 1. It cannot be greater than this. So if you get sine phi equal 1.2, this It means the linkage is going to stall at this specific point value of theta 2 type thing. So because theta 2 changes from 0 to 2 pi, so at some point in time you expect theta 2 to be equal to 1, and then in this case sine phi will be equal to r2 over r3, and if r2 is over r3 is greater than 1, what will happen? Then the linkage is going to stall. Linkage will stall at values above r2 over r3 sine phi 2 sine theta 2 greater than 1. 100% is going to stall. So like if you think in terms of drawing, so like here, and this was r3, and this is r2, will come to a point where, and this is theta 2, you will get a situation in this case where the linkage will be like that, and here that's r2, r3, this is phi, and this will be as far as it can get, but like in terms of phi cannot be below, cannot fall below 90 degrees type thing. In this case, so this will be theta 2, and if the linkage allows this to happen, this means now the value at this situation here, I have r2 over r3 sine theta 2. Those together, all this product is equal to 1. All right, so that's here phi is equal to 90. Now it cannot go any higher than this, because when you think about it, if the crank wants to come here, the con rod doesn't have enough length to support moving to this position. So type thing. So it's going to stall at this point, and all because R2 is greater than R3 type thing. And just I could tell from the equation that I'll get a sine value greater than 1, and to me this is not good at all. If R2 was equal to R3, like here, if R2 was equal to R3, like R2 over R3 was equal to 1, what happens then? I have at some point in time, this will be sine phi will be equal to sine theta 2 type thing, and then so this linkage are equal, those are equal like that, right? And then I'll find that I'll have a situation where the whole thing falls on top of each other like that. If this is R2 is equal to R3 at theta 2 equal 90, phi is equal to 90 as well, and then you'll find that the whole linkage collapses to one line. The linkage collapses to a single line. And this is a singularity, of course. That's a singularity you don't want to have in your linkage, right? So because after this point here, you don't know if the crank comes to this point, you don't know exactly what will happen, where like if the crank is trying to move further from this point here, you don't know exactly where the slider will go, right? Like in the right direction or left direction type thing. And then we get two possibilities for the location of the slider at this stage, and these two possibilities indicate the presence of a singularity, which mathematicians refer to as bifurcation, if you like. Now let's have a look at another example, which is a 4-bar chain. All right, for a 4-bar chain, I'll just try to get a drawing I had from previous lecture and insert it here. So go insert figure, and file and see if I can get my 4-by-chain file here. All right, so that's my 4-by-chain. I'm going to move it here and use it for my analysis and give you this example. I want to get some equations as well. So over here, I will try to, so this is my 4-by-chain. I'll just maybe flatten this with, make it a little bit bigger. I can write inside it and then just flatten it with my page so it doesn't move around. All right, so with this 4-part chain, my input here is the angle theta 2 one more time. So that's my input here, the angle theta 2. And what I'm trying to find is the angle theta 4 of the rocker. And quite possible also, I'd be interested in finding the angle theta 3 of link number 3 of the conrod of the coupler, and then I would have found this way all the possible like the positions or the angles of different links I have in the linkage. I've done this before in the previous lecture where I could actually prove we had two possible assemblies if you like. So that's this one, the assembly above here was this is the crank which works for both assemblies, and then the conrod the coupler is here in the first assembly. The second assembly, the coupler was the green one, and the rocker here was this is the first assembly. So I'm just working on the one assembly type thing. Right, okay. Now I wanted to find, based on theta 2, the values of different angles and so on. So I'll start by drawing, creating a triangle because I'm using trig. So I want to have a triangle here. So go insert a straight line, possibly just change the color of that a bit. So I'll have a straight line, this straight line here, right? Sort of thing. So I have this straight line from here to there, right? So this line I'm going to flatten as well. Right, so this is my line. So I'm going to call this line, I'm going to say this line, I'm going to call it, give it the name L. So that's L here. And this will be an angle phi I'm going to use in my analysis. All right, so now, and right, so let's say I can calculate the value for L based on my triangle. I can say L squared is equal to R2 squared, right? And this here is R1, so that's R1. So plus R1 squared minus 2 R1 R2 cosine the angle that falls between them, which is cosine theta. So this gives me an expression for the length L. All right, from the length L, I can get another, the angle phi. I can, for this angle phi, I expect the angle phi to fall to be plus and minus, right? If it falls like that, or because what will happen then, the crank, don't forget that point A falls on this circle, rotates on the circle, and at some point in time, it will come, it will be here below the x-axis, and then the length, the L, will fall also below the x-axis. So we'll find that phi will have a negative value as well. So like I expect phi to be plus or minus. So I expect phi to be in these quadrants. So in this case, I need sine to find it. I think we agreed on this previously. So I need sine minus 1. So I need a sine expression for phi. So I can say, okay, phi, sine phi over the opposite, which is R2, is equal to sine theta 2 over L. And this gives me an expression for phi. So sine phi is equal to R2 over L sine theta 2. And then this gives me an expression for phi. So I can go phi is equal to sine minus 1 R2 over L sine theta 2. And this gives me a value of phi based on theta. When theta is above the when the crank is above the x-axis, theta will be like from 0 to pi, you'll get positive value. And then when it goes, when point A starts to go dive below the x-axis, then you get values for theta 2 above pi, then you get negative value inside here, so you get a negative value for phi, which tells me phi will be below the x-axis. So everything works together nicely at this stage. Now, what if I wanted to find, so by the way, this angle phi is repeated, it's here as well, isn't it? This is the same angle phi. Okay, that's an angle phi here. Right, okay, so phi, both angles here, that's phi. So this little angle is actually phi as well. Now, if I want to get this other angle here, because this angle will possibly, if I get this angle and take phi from it, I can get theta 3 for the coupler. So let's call this angle lambda for now, right? So this is the angle lambda for now, right? By the way, this angle lambda is equal to the angle lambda below it, right? Sort of thing, because it's like for in the other assembly, which is not important. I'm not looking at this assembly, I'm just alerting you to the fact that like for the other assembly, you get the same angle alpha, and maybe you get also. All right, so let's get calculate lambda then. Then lambda, I expect lambda to fall just will be which range? Will be in the from 0 to pi type range. So I expect the angle lambda to fall in those two quadrants. So from quadrant 1 to quadrant 2. So lambda will be here in this range, right? So I can use cosine to calculate my lambda, log cosine minus 1. So let's find an expression for lambda. So I can, if I go r4 squared, and a cosine expression will do. So if I go r4 squared, here r4 squared is related to r3 and to L. So that's equal to right? So it's equal to r3 squared plus L squared minus 2 r3L cosine the angle lambda. Is this correct? All right, so here, right, this will be cosine the angle lambda, and then I can get an expression for cosine lambda if I want to. So I go cosine lambda, that's equal to, right, r3 squared plus L squared minus R4 squared over 2 R3L. That's cosine lambda, and lambda is equal cosine lambda is cosine minus 1, this sort of expression here. So it gives me an expression for lambda. If I want theta 3 at this stage, just go theta 3 is equal to the whole of lambda, take away phi, right? That's 1. So theta 3 is lambda minus the angle phi, which I had just calculated. I calculated previously here. So this is my angle phi. So as a function of theta, at the value of theta, I calculate my L. That's L initially, and then from L, I plug L here, get phi, so I get the value of phi, and then I move on to get same L, I get the value of lambda, and then take lambda 5 from lambda and get my value of theta 3. So I get the position or the angle of the cone rod. Okay, that's good. Now, if you are looking at the other assembly, you can also get from the same lambda, you can get theta 3, right? If you want to get the angle theta 3 for the second assembly, it will fall below the x-axis. You can call it negative if you like, which will be like sort of, or you can say if you measure theta 3 for the other assembly, you just go the whole 2 pi and then take from 2 pi phi, and you take lambda from 2 pi for the other assembly if you are interested in. For I just write on the side for those who are initiated. For assembly number 2, and theta 3 will be 2 pi, take lambda and take phi, and just double check it and check this and make sure it makes sense, that thing. All right, so now if I want to get my theta 4, I need to find another angle. Possibly let's call this angle gamma. So this angle gamma here. And then from phi and gamma, those two angles, and the pi, I can get theta 4. So let's find an expression for angle gamma. I possibly can also use a cosine expression for gamma, because again it will fall between 0 and pi, just like lambda would, type thing. Right? So it's sort of range. So I can also use a cosine expression. So I start by r3 squared for lambda. So then I go r3 squared will be equal to r4 squared plus l squared. Okay, it makes sense. Okay, r4 and l minus 2 r4l cosine lambda, and then I can get an expression for no, this one was gamma, in fact, sine gamma, and then I can get an expression for cosine gamma by saying, okay, it is r4 squared plus l squared minus r3 squared over 2 r4l. So get gamma from cosine minus 1. So this gives me an expression for the angle gamma, which is the angle subtended here. Just use a different color. I managed to get it. Then it will be this angle in gray. Now, if I want theta 4, I just take the sum of those angles, gamma and phi, from pi. So I can go theta 4 now is pi minus gamma minus phi. At this point in time, I have my theta 3 and I have my theta 4 as well. And if you want to get theta 4 for the other assembly, if you like, if you are interested, it will be, because other assembly, theta 4 is the whole lot that goes to here. So it's really will be equal to like pi, and you add to pi this distance here, this little bit, this angle here, which is equal to gamma minus phi, right? So for the other assembly, for assembly 2, let's just for those initiated again, just assembly number 2, theta 4 is equal to pi, add to this uh, gamma, right? So add gamma, because gamma is equal to this whole lot, so that's minus phi. So this little bit here is gamma minus phi. So I'm just adding this to, I think so, plus gamma minus phi. So this will be for assembly 2 for those who are interested. So in any case, at this point in time now, I have found expressions for the angles of theta 3 and theta 4, and I can plot those expressions against theta 2, which is a crank angle, if you like. And I have put together a MATLAB file which does this for you, and I'll get you to have a look at shortly. I'll put this also on Moodle for you, the MATLAB file, and just run it and have a look at how it works. You change values and see what values you obtain when you run the file. All right, so this here is the MATLAB file which does the analysis for you for a 4-bar chain. And then here I input my dimensions for the 4 links, and I input my values for theta 2. So theta 2 is inputted here, and I'm trying to input an array of theta 2, which starts from 0, and then here, like, it's this equivalent to 1 degree, but in radians. So like pi over 180, and then 2 pi over 180, and so on, like sort of till it's 2 pi, right? It's okay, so it's 2 pi. And then this will be an array of theta 2. Why? Because I want to study what will happen with, as the crank moves, what will happen to those angles I have inside my linkage. Now, don't forget, if you do this graphically, then the time and the effort, like, because now I'm just turning the crank 1 degree at a time to look as at what will happen. Now imagine doing this on AutoCAD or whatever graphically. So computer, of course, if you program, if you know the equations, you know them, you have done an analytical solution, and then for the position analysis, and you apply this in a computer program, you get a good insight with, if you like, when you save plenty of time, like immense amount of time. Here, just over here in my folder or my file here, I am uh, just getting obtaining how many points I have in the array theta 2, right? That's how many points I have just by using the length function, which is a um, MATLAB function. Now, I didn't use this specific n, like the number of entries in my program. I use it later on in another program when I did animations and other things. But okay, so I didn't need it here, but I thought maybe keep it so you guys know how to get the length of an array, because you'll need this later on. This is where I get to calculate the length L, which is very important, finding those other values for angles for me. And I just wanted to say here, this is a square root of the expression I had. Now, don't forget that theta 2 is an array of values, many values for thetas, right? So expect also L to be an array of many values, where every value will correspond to a specific value of theta. Just to say, I want to take every value in an array theta 2 and use it to calculate L. When I do the multiplication here, the asterisk, but the star is multiplication side. If you, I want you to note the dot, the little dot I have here. So this little dot ensures that every element is taken from the array separately and used in this calculation to give me a corresponding value in the array of L. So this dot again is used when I want to calculate, and I'm calculating phi here, just getting phi from the sine value, as we agreed. So this is sine phi, and instead of here I just call it s phi, and s phi is like a store in the memory of the computer, in which I'm going to store, if you like, or to save the values of sine phi. And this is how I calculate my sine phi. All right. So remember, it was R2 over L sine theta 2. And because now this is over L, but L was an array, so I want to take every value from the array. So I use, you see, this is divided by, but I used here the dot, and here, and times sine theta 2, and theta 2 as an array, so I use the dot again. So what happens is this specific function will grab from the array theta 2 and the array L the corresponding matching terms and or entries, and put them here, and will give me an array called S phi, this array, and will have different lots of different values for sine phi, and then I get phi from sine phi. So this will be an array as well. This phi 100% will be an array, because it will take every value from sine phi, every entry, and give me a corresponding value of phi. Here I'm calculating my angle lambda from the cosine minus 1, and I'm getting my theta 3 for assembly 1, and just lambda minus phi. Don't forget also, when I get lambda, I have an array of lambda because theta 2 changes. So I use the dots over here in my expression just to do the array thing. All right. Okay. Now, and here I'm calculating gamma, and I'm getting gamma from cosine minus 1 gamma. And I'm saying that I'm giving you the things in green are just comments, and I want you to have a look at those comments, because it tell you, I could, if I'm not sure about the range of sine phi, or where phi is going to fall, or the domain of phi, I would use sine and cosine together and use a function called the a tan2, like this function here, right? But because I was sort of, sure they will fall, the angle phi is going to fall in this range, so I thought sine would be sufficient for my calculations. Over here, I calculate theta 4, and then for assembly 1, and then I decided to put whatever values for angles and phi and theta 4 and theta 3 or whatever in plots. So I put them in a subplot, and subplot is where you get to draw like things like that, and you have different plots on the same graph, and they call them subplots. So because that's subplots, here I have one here, because 3 stands for 3 plots on the one line, and so this is one. First one means a line, so one line, and 3 means number of plots per line, and the second line means the second one to the right of 3 means I'm talking about the first plot. And then when I do the second plot, you'll find that I have here a second plot. I'll be talking about second subplot. We'll be talking about here this one here. So it's one. I have two because this is the graph, third plot, and here I have three, the third plot. And this just gives you what I plot in every one, and I have lots of comments written in green for you guys to understand what I'm doing here. So please, this will be on a model. Try to do it. Try to learn those equations and do other examples as well. Possibly in the next lecture we'll do another example quickly for you, and then next lecture we'll also talk at using the vector methods to do our position analysis, obtain equations like analytically. All right, thanks very much, and do as many examples as possible. If you get stuck, please drop us a line either on Moodle or email. Good luck.